In this video, we'll be talking about the final presentation for the Grand Challenge and what it is all about. The objective of the Grand Challenge is to design a rover-alike system that aids in locating and moving supply drops for the first explorers in their attempt to build and colonize Mars. We will also be seeing the various parts that we'll be using to build the robot. The first one is the Berry IMU, which is a 10 DOF board, which is used as to locate the heading and find the heading of the robot. The Raspberry Pi, which is used as a controller to control the motors and the various sensors and do all the processing for the robot and give out commands. The ultrasonic, which is used to find the distance between the robot and the surrounding objects so that it can do obstacle avoidance. The H-bridge, where it's used to control the direction in which the DC motors run, and the various connections that the Raspberry Pi has. Next, we will be looking at the OpenCV module using the Raspberry camera, and the camera is used to find a certain color based on what it's given and find the region of interest that it needs to locate and find the orientation or any other aspects of the object that we need to track. This video shows a brief example of how it is used and how it actually tracks an object. We will be seeing a much bigger example in the later part of the video. The next part is about the assembly of the robot. The robot that we'll be using is a Pirate 4WD robot, and is fitted with 4 DC motors with encoders in the front left motor and the back right motor. This images actually show you how the robot looks after a full assembly that is being done to it, and how the the Raspberry Pi is connected to all the sensors on board, and how the battery pack is connected to the robot. In this section, we'll be seeing about the tele operation of the robot from a computer. The code is written in Python, and it's written in such a way that you will be able to send certain commands to the robot through a computer, which it follows and makes the turns based on the commands that you give and moves forward or backward. As you can see, when the robot moves, it makes some kind of an error based on the slippage or based on the surface that it moves. So we will be looking at how to tune the robot in this section, and we will in this section we will be also showing how the code has been modified to prevent the robot from going off to the right or left, or veering off to the right or left, and how it actually follows a certain distance that is given to it as a command, and the turning angle and the turning of the robot to a certain direction is also controlled using. As I said, one of the major disadvantages that I faced when I was tuning the robot is to make it turn right or left without any errors, which is mostly caused due to the slippage of the robot and the way the weight distribution is done on it, so that the pressure on one wheel is more than the pressure on the other wheel, which actually in turn leads to a floating of the wheel and in turn leads to slippage. The robot is actually fine-tuned in such a way that it can actually do this, and we actually made it possible for the robot to track its movement and make it possible to plot its trajectory out. So this video actually shows how the robot moves and how the accumulated error makes it an issue for the robot over a period of time when it is moving, and this has been corrected and will be shown and is shown here. The fine-tuning of the robot was actually a big hassle, since it was fine-tuned to a certain surface, and it keeps changing from surface to surface, and it has to be calibrated if you're going to move a robot on a different surface. And we have to keep in mind that the encoder of the robot also keeps changing, and over a period of time it kind of gets loosened up, so we have to make it much more fastened so that we can have a very accurate measurement of the trajectory of the robot. This video shows a random movement of the robot, which I kind of fed into the system for an autonomous execution, or not an autonomous execution but a continuous execution. The plot of the robot will be shown after the video ends, where it shows how it actually moves and tracks the robot over a period of time where it moves. This video also shows how any minute errors caused in even a minute change will be a big effect on your end position or end goal that you supposedly reach, or the robot thinks it supposedly reached. In this part, we will be talking about the OpenCV part, which I mentioned before, for tracking of an object that we need. In this, the robot has been given a color of red, where it finds its region of interest by masking it and finding the area in which it is located in a single frame, and it enables us to move or try to align the robot towards the object so that it's easier to pick up. This video shows how the robot actually follows the object when it is moved over a period of time, and how it actually tracks it with the frame coordinates that is calculated from the image that we have and the place at which the ROA actually is at. In this, we will be looking at the final bot that has been designed for the Grand Challenge. So for the Grand Challenge, I've added a couple of sensors, ultrasonic sensors, and changed the existing position of the ultrasonic sensors from the breadboard to the bottom of the servo motor, or the bottom of the gripper, where it can actually see the base of the object that we have. And the additional ultrasonics are mounted on the top front and as well as the top left of the robot, so that it can eliminate all the shortcomings of misleading objects that is being recorded or identified. This also enables us to move much faster on locating and going to an object. So this video is an output from my Grand Challenge, and how my robot actually tracked a red block from the middle and try to pick it up. The robot uses an IMU to find its heading that it is currently on and tries to get to a reference position after it has picked up the robot, where I have set the reference position to a left turn of 90 degrees and tries to home itself back to the construction zone or where it's supposed to go to. The robot actually makes a lot of errors in this due to a lot of accumulated errors, as well as the erroneous values that you get from the IMU and the distance sensors. And this I would state as the largest reason of my shortcoming of the video. Last but not, this slide shows the software architecture of the robot for the Grand Challenge. The explanation or each block is given in the PPT. This clip goes as a tribute to the professor of the course, to one of the most intelligent as well as one of the most friendliest and coolest professors that I've worked till date. Thank you for making it a fun and memorable course. Thank you for watching this video.